The year was 2003, and Nick Bostrom sat alone in his office at Oxford University, staring at a document that would eventually reshape how humanity thought about existence itself. The Swedish philosopher had spent months wrestling with a thought experiment, one that had kept him awake through countless nights in his small apartment near the Bodleian Library. His paper, titled "Are You Living in a Computer Simulation?" was about to introduce the world to the simulation hypothesis in its most rigorous form. Bostrom's argument was deceptively simple. He proposed that at least one of three propositions must be true: civilizations almost always go extinct before reaching the technological capability to create reality simulations; civilizations that reach such capability choose not to run such simulations, or we are almost certainly living in a computer simulation right now. The mathematics were elegant, almost unsettlingly so. If any civilization anywhere in the universe ever develops the computing power to simulate consciousness, and if they run even a modest number of such simulations, then the number of simulated beings would vastly outnumber biological ones. The odds, Bostrom concluded, would overwhelmingly favor any conscious entity being simulated rather than original. What Bostrom perhaps did not anticipate was how his academic exercise would resonate with experiences that humans had been recording for millennia: strange occurrences that seemed to suggest glitches in the fabric of reality itself, patterns too precise to be coincidental, and moments where the universe appeared to behave less like nature and more like code. The ancient Greeks had a word for it: aletheia, truth as unconcealment, the pulling back of a veil. Plato, writing in Athens around 380 BCE, described prisoners chained in a cave, watching shadows on a wall and believing these shadows to be the totality of existence. The allegory of the cave, as it came to be known, proposed that what we perceive as reality might be nothing more than projections, dim reflections of a truer existence that lies beyond our perception. For centuries, scholars treated this as metaphor, a philosophical teaching tool. But what if Plato was describing something more literal than anyone realized? In the summer of 1982, a physicist named John Wheeler stood before an audience at the University of Texas at Austin and proposed something that would have seemed absurd from any less distinguished source. Wheeler, who had coined the term black hole and collaborated with Albert Einstein on the foundations of general relativity, suggested that the universe might be fundamentally informational in nature. It from bit, he declared, meaning that every particle, every field of force, even the fabric of spacetime itself, derives its existence from the answers to yes or no questions, from binary choices, from information. The universe, Wheeler proposed, might be built not from matter or energy as its base reality, but from pure information, ones and zeros, the same building blocks that would later compose every video game, every digital simulation, every virtual world that humans would create. Wheeler's proposal gained unexpected support from an entirely different direction. In the 1970s, Jacob Bekenstein, a Mexican-Israeli physicist working at the Hebrew University of Jerusalem, discovered something peculiar about black holes. The amount of information that could be contained within any region of space was not proportional to its volume, as intuition would suggest, but to its surface area. This was strange. If you had a cubic meter of space, you would expect it to hold more information than a square meter. But Bekenstein's calculations, later confirmed and extended by Stephen Hawking, showed that the maximum information content of any region was encoded on its two-dimensional boundary, not distributed through its three-dimensional interior. The implications were staggering. Our three-dimensional universe might be a projection, a hologram arising from information encoded on a distant two-dimensional surface. The holographic principle, as it became known, suggested that the depth and solidity we experience might be illusions, sophisticated renderings generated from a more fundamental flat reality, exactly as a three-dimensional video game is generated from two-dimensional code running on silicon chips. Juan Meldacena, an Argentine theoretical physicist working at the Institute for Advanced Study in Princeton, would later provide mathematical proof of a specific version of this principle. In 1997, Meldacena demonstrated that a particular type of five-dimensional universe could be exactly equivalent to a four-dimensional theory on its boundary. The physics inside the higher dimensional space could be completely derived from simpler physics on the surface, like a hologram containing all the information needed to reconstruct a three-dimensional image. When other physicists verified and extended his work, the idea that our universe might be a projection began its transition from speculation to serious scientific consideration. But, long before these mathematical proofs, human beings had been experiencing phenomena that seemed to reveal cracks in reality's facade. The feeling of déjà vu, the uncanny sensation of having lived through a moment before, has been documented across virtually every human culture. The term itself was coined in 1876 by Émile Boirac, a French psychic researcher, to describe a phenomenon that had puzzled humans for as long as they had words to describe it. Standard explanations involve memory misfiring, the brain accidentally tagging a new experience as a memory. But, the subjective experience often feels different, less like a memory error and, more like recognition, as if the present moment is running a second time. In 1896, Arthur Allen, an American psychologist, interviewed dozens of subjects who had experienced intense déjà vu episodes. One recurring theme struck him: many subjects described not just familiarity with the current moment, but a brief sense of knowing what would happen next, as if they had access to a script. The feeling typically dissolved before they could act on this foreknowledge, leaving only the eerie residue of having glimpsed behind the curtain. The Matrix, released in 1999 by the Wachowski sisters, transformed simulation theory from philosophical abstraction to cultural phenomenon. The film depicted a future in which the reality experienced by billions of humans was actually a sophisticated computer program, a neural interactive simulation designed to keep their bodies docile while machines harvested their bioelectricity. The scene in which Keanu Reeves' character Neo sees a catwalk by twice, identical in every detail, and is told that such déjà vu indicates a glitch in the Matrix, resonated with audiences in a way that surprised even the filmmakers. People recognized something in that moment, a cinematic articulation of experiences they had quietly wondered about for years. What the Wachowskis likely did not know was that their glitch in the Matrix scene would spawn an entire genre of personal accounts. Within years, internet forums would fill with stories from people describing experiences that seemed to defy normal explanations, objects appearing in places they could not have been, small changes in familiar environments that others did not notice or remember, moments when reality seemed to stutter or reset. One of the most documented categories of such experiences involves what has come to be called the Mandela effect, named after a strange collective memory concerning the death of Nelson Mandela. Fiona Broom, a paranormal researcher, first described the phenomenon in 2009 after attending a convention and discovering that she shared a specific false memory with numerous other attendees. They all remembered Nelson Mandela dying in prison in the 1980s, remembered news coverage of his funeral, remembered the morning of a nation. But Mandela had not died in prison. He had been released in 1990, had become the first democratically elected president of South Africa in 1994, and was very much alive in 2009. He would not die until December 2013. The standard explanation for the Mandela effect involves confabulation and social reinforcement of false memories. Human memory, psychologists point out, is reconstructive rather than reproductive. We do not replay recordings of past events, we rebuild them each time we remember, filling in gaps with assumptions and suggestions. When many people share similar false memories, it may simply reflect common cognitive patterns and shared cultural references, creating similar errors across populations. But the specific details of these shared false memories prove more difficult to explain. In the case of the Berenstain Bears, a popular series of children's books, millions of adults remember the name being spelled Berenstein. They remember the cursive letters on the book covers, remember sounding out the name as children, remember the way it rhymed with other words ending in Stein. The actual spelling, Berenstain, feels wrong to them, feels like a recent change. Stan and Jan Berenstain, the authors, had always spelled their family name that way, a variant reflecting their Yiddish heritage. Yet the collective memory of an alternate spelling persisted, vivid and specific. Similar shared memories emerged around dozens of other cultural touchstones. Many people remembered the comedian Sinbad starring in a 1990s children's movie called Shazam, in which he played a genie. No such movie exists. Sinbad himself has addressed the phenomenon multiple times, confirming that he never made such a film. Yet the memories persist. People describe the cover art, recall scenes from the movie, remember watching it on VHS as children. Proponents of the simulation hypothesis suggested an explanation that was either brilliant or absurd depending on one's philosophical commitments. Perhaps these memories were not false at all. Perhaps they were artifacts of changes to the simulation, updates or corrections to the program that most people's memories adjusted to accommodate, while some retain traces of the previous version. The universe is a living document, subject to revision, with some readers noticing where the eraser marks remained. The physics of the very small seem to offer its own evidence for a simulated reality. In 1927, Werner Heisenberg, a German physicist working in Copenhagen, formulated what became known as the uncertainty principle. The more precisely you measure a particle's position, Heisenberg showed, the less precisely you can know its momentum, and vice versa. This was not a limitation of measurement technology, it was a fundamental feature of reality itself. Particles did not possess definite positions and momenta that we simply failed to detect. They existed in states of quantum superposition, simultaneously occupying multiple positions, until the act of measurement forced them to assume definite values. The behavior was uncannily similar to a particular technique used in video game design, level of detail rendering. Modern video games do not fully render objects that players are not looking at. Instead, they maintain those objects in simplified or probabilistic states, conserving processing power, and only render full detail when the player's attention turns toward them. The universe, quantum mechanics suggested, behaved the same way. Reality was not fully resolved until observation demanded it. Eugene Wigner, a Hungarian-American physicist who would win the Nobel Prize in 1963, pushed this idea further. In 1961, he proposed a thought experiment known as Wigner's friend. Imagine a physicist performing a quantum measurement inside a sealed laboratory while his friend, Wigner, waits outside. According to standard quantum mechanics, the particle being measured exists in superposition until observed. But, from Wigner's perspective, isn't the entire laboratory, his friend included, in superposition until Wigner himself opens the door and looks? The thought experiment suggested that consciousness might play a fundamental role in determining reality, that observation was not merely passive detection but active creation. John Wheeler proposed an even more disturbing variant called the delayed choice experiment. In Wheeler's thought experiment, later confirmed in actual laboratory experiments, the decision to observe a particle in a certain way seemed to retroactively determine how that particle had behaved in the past. Light that had traveled for billions of years from a distant quasar would behave as if it had known what measurement a scientist would perform in a laboratory on Earth, adjusting its historical behavior to match observations that had not yet been made when the light began its journey. The experiments seemed to suggest that reality was not computed in advance and merely discovered by observers. Instead, it might be generated on demand, rendered in response to queries, its history backfilled to maintain consistency. This was exactly how sophisticated simulations would need to operate, maintaining the illusion of a continuous pre-existing reality while actually generating details only when required. In 2012, Silas Bean, a nuclear physicist at the University of Bonn, along with colleagues Zare Davudi and Martin Savage, proposed a method to test whether our universe might be simulated. They noted that any simulation would likely employ a discrete lattice structure, dividing spacetime into small but finite units rather than truly continuous fabric. This lattice would create subtle observable effects. Cosmic rays traveling through the universe would have slightly different energies depending on the size and orientation of the lattice. The highest energy cosmic rays would reveal the pixelation of spacetime, if such pixelation existed. The results of subsequent observations proved ambiguous. Some measurements seemed consistent with a lattice structure, others did not. The universe appeared to guard its secrets carefully, revealing just enough anomalies to fuel speculation while withholding definitive proof. But, if the universe were simulated, who or what was running the simulation? And why? In August 2016, at a dinner during the Code Conference in California, the technology entrepreneur Elon Musk offered his thoughts on the matter. Musk, who had made his fortune with PayPal, Tesla, and SpaceX, had clearly spent considerable time contemplating the simulation hypothesis. His argument paralleled Bostrom's but approached it from a technologist's perspective. 40 years ago, Musk noted, the most advanced computer game was Pong, 2 paddles and a ball. Now we have photorealistic simulations, virtual reality headsets, games that are nearly indistinguishable from the physical world. Project the trajectory forward another 10,000 years, assuming civilization survives, and the games would become indistinguishable from reality in every measurable way. Given enough time and computing power, Musk concluded, the odds that we are living in base reality were 1 in billions. The dinner guests, some of the most prominent figures in Silicon Valley, reportedly fell silent. Here was a man who had dedicated his life to pushing the boundaries of technology, who spent his days designing rockets and electric vehicles, suggesting that the physical world might be nothing more than software. Musk later added that he and his brother had instituted a rule: they would not discuss simulation theory while in hot tubs, because the conversations became too disturbing. The simulation hypothesis attracted supporters from unexpected quarters. Neil deGrasse Tyson, the astrophysicist and director of the Hayden Planetarium, publicly stated that he gave better than 50-50 odds that we live in a simulation. The late physicist Freeman Dyson, who had worked on quantum electrodynamics with Feynman and Schwinger, found the idea intriguing rather than absurd. Even Stephen Hawking, in his final years, acknowledged that the hypothesis could not be dismissed on purely scientific grounds. But the most striking evidence for simulation theory came not from physics or philosophy but from the deep structure of mathematics itself. In 1960, Eugene Wigner published an essay titled The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner, writing from his office at Princeton, expressed wonder at a phenomenon that most scientists took for granted: the universe obeyed mathematical laws. The orbits of planets followed equations. The behavior of atoms matched predictions derived from symbolic manipulation. Physical constants could be expressed as precise numbers. Why, Wigner asked, should abstract mathematical structures invented by human minds correspond so exactly to the behavior of physical reality? The question had no satisfying answer. Darwin's theory of evolution might explain why human brains were good at intuitive physics, why we could catch a thrown ball without solving differential equations. But it could not explain why differential equations, arbitrary-seeming abstract constructions, should describe the trajectory so perfectly. Natural selection might produce brains optimized for survival. It should not produce brains that accidentally discover the source code of the universe. Unless, of course, the universe was made of mathematics because it was generated by mathematical processes, because it was, in the most literal sense, a computational object. Max Tegmark, a cosmologist at MIT, proposed precisely this. In his 2007 paper and subsequent book, Tegmark argued for what he called the mathematical universe hypothesis. The universe does not merely obey mathematical laws, it is a mathematical structure. Physical existence and mathematical existence are the same thing. We perceive mathematics as abstract because we are embedded in one particular mathematical structure among many, seeing it from the inside rather than the outside. The implications were dizzying. If the universe is a mathematical structure, then it is formally equivalent to a computation. It could in principle be simulated by any system capable of performing the relevant calculations. It might even be self-simulating, a mathematical structure that contains within itself the means of its own instantiation. These ideas found unexpected resonance in the work of Konrad Zuse, a German engineer who had built one of the world's first programmable computers in his parents' living room in 1930s Berlin. In 1969, Zuse published a book titled Rechnender Raum, or Calculating Space, proposing that the universe was fundamentally a cellular automaton, a grid of discrete cells that update their states according to simple rules. Zuse suggested that what we perceive as physics was actually computation, that particles and forces were patterns in a cosmic computer program. The book received little attention at the time. But, when computer scientists began seriously exploring the computational properties of physics in the 1980s and 1990s, they found Zuse's ideas remarkably prescient. Edward Fredkin, a former MIT professor, developed similar ideas independently, proposing that the universe operated as a gigantic digital computer. Stephen Wolfram, creator of Mathematica and author of A New Kind of Science, spent decades exploring how simple computational rules could generate complex behavior that mimicked physical laws. The digital physics tradition reached perhaps its most developed form in the work of Gerard 't Hooft, a Dutch theoretical physicist who had won the Nobel Prize in 1999 for his work on the electroweak force. In a series of papers beginning in the 2000s, 't Hooft proposed that quantum mechanics might emerge from a deterministic underlying reality, a cellular automaton operating at the Planck scale. The apparent randomness of quantum events might be illusion, the predictable output of a computation too fine-grained for us to resolve. If 't Hooft was right, the universe was not merely analogous to a computer simulation. It was one. But, what would it mean for human life if the simulation hypothesis proved true? What would be the existential implications of discovering that reality was rendered rather than fundamental? The philosopher David Chalmers, known for formulating the hard problem of consciousness, addressed this question in his work. Chalmers argued that discovering we lived in a simulation should not necessarily be considered bad news. A simulated apple, he noted, is still an apple. Simulated pain still hurts. Simulated love is still love. The experiences would remain real even if their substrate proved to be computation rather than atoms. We would simply have learned something new about the nature of the reality we had always inhabited. Others were less sanguine. The possibility that our simulators might terminate the simulation, whether deliberately or through accident, introduced a new category of existential risk. The simulation might be an experiment, and experiments end. It might be entertainment, and entertainment becomes boring. It might be a scientific model, and models get updated or replaced. The entire history of human civilization, all our art and science and love and suffering, might exist at the pleasure of beings for whom we were merely patterns of information. This possibility haunted some who contemplated it. Preston Green, a philosopher at Nanyang Technological University in Singapore, argued in 2019 that humanity should not attempt to test the simulation hypothesis. His reasoning was chilling. If the universe is a simulation, and if our simulators have not bothered to make the simulation test-proof, then, discovering the truth might prompt them to terminate the experiment. We would be lab rats growing too clever, threatening to invalidate the research. Better to remain ignorant and alive than knowledgeable and deleted. The argument assumed that our simulators cared about the integrity of their simulation, that they did not want us to know the truth. But, other scenarios were possible. Perhaps the simulation was designed for us to eventually discover its nature. Perhaps that discovery was the point, the graduation examination of a simulated civilization. Perhaps our simulators wanted us to find them, were waiting for us to look up through the glass dome and wave. In the summer of 1996, a computer programmer named John Titor posted a series of messages on internet forums claiming to be a time traveler from the year 2036. Titor's posts were elaborate and detailed, describing a future shaped by civil war, nuclear conflict, and temporal mechanics. He explained that his time machine was built around many black holes, that it created closed time-like curves allowing travel to the past. Most of his predictions proved wrong, most spectacularly the Civil War he said would begin in 2004. The John Titor phenomenon faded into internet folklore, another hoax or delusion in the strange early days of the web. But, one aspect of Titor's posts attracted renewed attention as simulation theory gained popularity. He had described the universe as operating on a model similar to a computer program, with multiple branches of time coexisting simultaneously. Decisions created new branches, forking the program into divergent timelines. His time machine, he claimed, did not travel to the past of his own timeline but to the past of a parallel branch, a previous save point in a slightly different version of the simulation. The many-worlds interpretation of quantum mechanics, proposed by Hugh Everett III in 1957, described reality in strikingly similar terms. Everett suggested that quantum superposition never collapsed. Instead, every possible outcome occurred in a separate branch of a continuously splitting universe. The wave function did not reduce to a single state upon observation. Rather, observation created a branching point, with different versions of the observer experiencing different outcomes in different branches. Everett's interpretation had once been considered bizarre, a philosophical curiosity with no testable predictions. But, by the early 21st century, it had become the preferred interpretation among many theoretical physicists and virtually all cosmologists working on multiverse theories. The universe, it seemed, was constantly forking, generating new branches at every quantum event, like a program running all possible execution paths simultaneously. If the universe was a simulation running on quantum computational principles, the many-worlds interpretation suggested it was running not one simulation but an infinite number simultaneously, exploring every possible history, mapping every possible outcome. The branching structure would be not a bug but a feature, a way of parallelizing the computation, investigating all possibilities at once. The question of purpose remained. Why would anyone run such a simulation? What would justify the enormous computational resources required to model an entire universe at the quantum level? Nick Bostrom suggested several possibilities in his later work. The simulation might be a scientific tool, a way for an advanced civilization to study its own history or to model the development of intelligence and civilization. It might be an art project, the equivalent of a novel or a film, an elaborate fictional world inhabited by conscious characters. It might be an ethical experiment, an attempt to understand suffering and moral development by creating beings capable of both. Or it might serve purposes entirely beyond our comprehension, just as the purposes of humans would be incomprehensible to simulated ants in a simple ant colony simulation. The question of consciousness within simulations proved particularly vexing. Could a simulation generate genuinely conscious beings, or only philosophical zombies, entities that behaved as if conscious but lacked inner experience? The question touched on the hard problem of consciousness, the mystery of how subjective experience arises from physical processes. If consciousness was computable, if it emerged from information processing regardless of substrate, then simulated beings could be genuinely conscious. Their experiences would be real experiences, their suffering real suffering, their joy real joy. The simulation would be populated with moral patients, beings deserving of moral consideration, beings who mattered. This possibility imposed a strange recursive responsibility on humanity. If we ourselves eventually developed the capability to run ancestor simulations, detailed simulations of our own past containing conscious beings, we would face profound ethical questions. Would we have obligations to those simulated beings? Would running such simulations be an act of creation or an act of cruelty, bringing conscious entities into existence within constrained and often painful environments? The ethics of simulation became a topic of serious academic discussion in the 2010s and 2020s. If simulated suffering was real suffering, then creating simulations containing suffering was creating suffering. The game designers and virtual reality architects of the future might face moral dilemmas unknown to any previous generation. In 2003, the same year Nick Bostrom published his simulation argument, another philosopher made a different but related discovery. Derek Parfit, in a paper on personal identity, noted something peculiar about the probability calculations underlying the simulation hypothesis. If most conscious beings are simulated, then you should expect to find yourself to be simulated. But "you" here was ambiguous. The original Bostrom argument assumed a uniform probability distribution over all conscious beings. But what if simulated beings were somehow different from base reality beings in ways that affected the calculation? The objection opened a philosophical rabbit hole that has never been fully resolved. Personal identity, always philosophically treacherous, became even more complicated when simulated beings entered the picture. Could a simulation of you have your identity, your continuous experience, your first-person perspective? Or would it necessarily be a different entity, a copy, a twin who happened to share your memories and personality? The question had practical implications beyond the simulation hypothesis. As technology advanced toward brain scanning, neural emulation, and digital minds, the same questions would arise. If your brain were scanned and uploaded to a computer, would the upload be you? Would there now be two of you? If the biological original were destroyed during the scanning process, would that constitute death, or merely change of substrate? These questions consumed academic philosophy in the early 21st century, generating conferences, journals, and endowed chairs. But they also filtered into popular culture, appearing in films like Transcendence, 2014, and television series like Black Mirror and Westworld. The general public began grappling with questions that had once been confined to graduate seminars. The timing was not coincidental. As human technology advanced toward the capability to create realistic simulations containing what might be conscious entities, the question of whether we ourselves might be simulated became more pressing. We were approaching the threshold from the inside, developing the very technologies that might have been used to create us. In 2016, two researchers at the Fundamental Physics Group in California made an unexpected discovery while analyzing data from the relativistic heavy ion collider at Brookhaven National Laboratory. The collider smashed gold nuclei together at near light speed, briefly creating conditions similar to those just after the Big Bang. The researchers, James Gates and Sylvester James Gates Jr., were studying the mathematical structure of supersymmetric theories that might describe physics at these extreme energies. What they found was peculiar. Embedded in the equations were error-correcting codes of a type used in computer science. The codes, known as doubly even self-dual linear binary error-correcting block codes, were identical to those used in modern browsers and search engines to detect and correct transmission errors. The codes appeared in the mathematical description of fundamental physics, woven into the fabric of the equations that governed the behavior of matter and energy. Gates, a theoretical physicist at the University of Maryland, was initially reluctant to publicize the finding. The discovery seemed too strange, too suggestive, too easily misinterpreted. But, when he eventually discussed it in interviews and talks, it caused a sensation. Error-correcting codes were signature features of engineered systems, designed to maintain data integrity in the face of noise and interference. Finding them in the equations of physics was like finding copyright notices embedded in the source code of reality. Skeptics pointed out that the mathematical structures Gates identified might simply be coincidental. Complex equations contain many patterns. Some of those patterns will inevitably resemble structures used in other contexts. The universe was not obligated to avoid using mathematics that humans had also discovered. The presence of error-correcting code structures might reflect the universality of certain mathematical forms rather than deliberate engineering. But, the discovery added to a growing body of circumstantial evidence. The universe seemed to be constructed in ways that were startlingly compatible with computational interpretation. Quantum mechanics described a reality that behaved like rendering software. Relativity imposed speed limits reminiscent of bandwidth constraints. The holographic principle suggested that all information was stored on a two-dimensional boundary, like data on a hard drive. And, now, error-correcting codes appeared in the fundamental equations of physics. None of this constituted proof. The simulation hypothesis remained, in principle, unfalsifiable. Any evidence that seemed to support it could be explained as coincidence or misinterpretation. Any evidence against it could be explained as a feature of a sufficiently sophisticated simulation. The hypothesis was compatible with any possible observation, which made it either the ultimate theory or the ultimate non-theory, depending on one's philosophical standards. But, unfalsifiability was not the same as meaninglessness. The simulation hypothesis changed how we thought about existence, about meaning, about our place in reality. Even as speculation, it served a philosophical purpose. It forced us to confront the contingency of our existence, the possibility that the world was not as fundamental as it appeared, the humility of recognizing that our understanding might be radically incomplete. In March 2021, a group of physicists published a paper exploring what they called the simulation resolution problem. Any simulation must have finite resolution, it cannot compute an infinite amount of detail. The question was whether that resolution limit would be detectable from within the simulation. The researchers concluded that certain phenomena, particularly quantum effects at the smallest scales, might reveal the simulation's grain, the pixels of reality. They proposed searching for specific signatures, subtle violations of Lorentz invariance, the principle that physical laws are the same in all directions, anomalies in the cosmic ray spectrum at the highest energies, and peculiar statistical patterns in quantum measurements that might indicate pseudo-random rather than truly random number generation. The search for such signatures became a small but active research program, funding grants and doctoral dissertations, the scientific method applied to the most speculative of hypotheses. As of the early 2020s, no definitive evidence had been found. The universe continued to present itself as either genuine or an extraordinarily good simulation, a reality or a rendering so perfect that no seams were visible. Those who sought evidence of the simulation remained hopeful. Those who dismissed the hypothesis as meaningless remained dismissive. The question itself remained open, like a door that might lead somewhere profound or might open onto a blank wall. The human response to the simulation hypothesis proved as varied as humanity itself. Some found it terrifying, an assault on everything they valued, a suggestion that their lives and loves and losses were merely patterns in a program. The possibility that existence might be switched off, that their reality existed at the whim of unseen others, induced existential vertigo. Others found it liberating. If reality was a simulation, then, the constraints they had accepted as fundamental might be negotiable. The laws of physics might be parameters rather than absolutes, potentially modifiable by those who understood the system deeply enough. Death might not be final if consciousness was backed up somewhere, if the simulation maintained records of all who had lived within it. The simulation hypothesis offered, for some, a technological afterlife more plausible than religious ones. Still others found themselves indifferent. The experience of life, they noted, would remain the same regardless of its underlying nature. Food would still taste good. Love would still feel meaningful. Achievement would still satisfy. Whether those experiences were generated by neurons or by software made no practical difference. The simulation hypothesis changed everything and nothing. This diversity of response pointed to something important about the human relationship with reality. We had always lived within a representation, a model constructed by our brains from sensory data, a simulation of sorts running on biological hardware. The question of whether this internal simulation corresponded to an external physical reality or to another simulation was, in a sense, one level of abstraction removed from our direct experience. We had never had unmediated access to ultimate reality, we had always lived within the simulation that was our own consciousness. Philip K. Dick, the science fiction author whose works would later inspire films like Blade Runner and Total Recall, spent his final years obsessed with the nature of reality. In a famous 1977 speech in Metz, France, Dick declared, "We are living in a computer-programmed reality, and the only clue we have to it is when some variable is changed, and some alteration in our reality occurs." Dick described personal experiences of what seemed to him like reality shifts, moments when details of the world changed in ways only he seemed to notice. Dick died in 1982, long before the simulation hypothesis entered mainstream scientific discourse. But his intuitions, expressed through decades of fiction exploring false realities and artificial worlds, anticipated themes that would dominate philosophical and scientific discussion decades later. His novel Time Out of Joint, 1959, depicted a man living in a constructed reality. Do androids dream of electric sheep? 1968 questioned what made beings real, and UBIK 1969 presented a world where the nature of reality remained permanently uncertain. Dick's work suggested that the simulation hypothesis addressed something deep in human psychology, a persistent suspicion that things were not as they appeared, that the world was stranger and more contingent than everyday experience indicated. This suspicion appeared across cultures and, throughout history, in Gnostic beliefs about a false physical world created by a flawed deity, in Hindu concepts of Maya, illusion, in Buddhist teachings about the constructed nature of experience. The simulation hypothesis was, in this sense, the technological update of a perennial human intuition. What ancient traditions had expressed in religious and spiritual terms, contemporary thinkers expressed in the language of computation and information theory. The glass dome was a new name for an old suspicion, the sense that we were surrounded by a construction, that reality had edges, that we were not seeing the full picture. In 2019, Rizwan Virk, a computer scientist and video game developer, published a book examining the simulation hypothesis from the perspective of someone who had actually built virtual worlds. Virk's background gave him practical insight into the challenges of simulation, the computational resources required, the techniques used to create convincing illusions, the shortcuts employed to reduce processing load while maintaining apparent realism. Virk identified 10 stages of simulation technology, from simple text adventures to fully immersive virtual reality indistinguishable from physical existence. He noted that video game development had progressed through most of these stages in just 4 decades. If progress continued, full simulation capability might be achieved within another century, possibly sooner with advances in quantum computing. The timeline was short enough that humanity might both be simulated and create its own simulations within historical memory. The recursive implications were dizzying. A simulated civilization creating its own simulations would generate simulations within simulations, nested realities of unknown depth. Each level would be convinced of its own fundamentality. Each would face the same questions about the nature of its existence. The simulation hierarchy might extend indefinitely upward, with no base reality at all, just simulations simulating simulations in an infinite regress. Or perhaps there was a base level, a true physical reality from which all simulations ultimately derived. The question of whether such a base level existed, and whether it could in principle be detected from within a simulation, remained open. Some philosophers argued that the question was meaningless, that physical and simulated were simply different descriptions of the same mathematical structures, and that the distinction between them was less significant than it appeared. The debate continued into the 2020s, enriched by advances in both technology and philosophy. Machine learning systems became increasingly capable of generating realistic images, text, and soon video, demonstrating how convincing simulations could arise from relatively simple algorithms. Virtual and augmented reality technologies improved steadily, approaching the quality thresholds that might eventually make simulated environments indistinguishable from physical ones. The simulation hypothesis remained unproven, but the technological trajectory that would make such simulations possible became increasingly clear. In February 2024, at a small gathering of philosophers and physicists in Cambridge, Massachusetts, a debate was held on the question, do we have any reason to believe we are not living in a simulation? The arguments were sophisticated, drawing on quantum mechanics, computational complexity theory, and philosophy of mind. No consensus emerged. The question remained as open as it had been when Bostrom first posed it, 2 decades earlier. But something had shifted in those 20 years. The simulation hypothesis had moved from philosophical curiosity to mainstream consideration. It appeared in scientific journals and popular science magazines, in TED Talks and late-night television. It had become part of the cultural conversation about the nature of reality, joining older questions about God and free will and the meaning of life. Perhaps this was the most significant impact of the simulation hypothesis, not any specific conclusion it supported, but the questions it forced us to ask. What is the relationship between computation and reality? What makes something real in the first place? What would it mean for our lives if they turned out to be computed? How should we treat beings within simulations we create? These questions would not go away, regardless of whether the simulation hypothesis itself proved true or false. They pointed toward deep issues that humanity would need to grapple with as technology advanced, as virtual and physical increasingly blurred, as the power to create worlds came within reach. The glass dome, whether real or metaphorical, had changed the view. Looking up at the sky, one might now wonder not just what lay beyond the stars, but what lay beyond the stars' rendering, beyond the night sky's display, beyond the entire construct that presented itself as a universe. The question was unanswerable, at least for now. But asking it had already transformed our understanding of what existence might be. We stood at the boundary of the knowable, peering through glass that might be transparency or might be screen. The image on the other side might be truth or might be simulation. The distinction, once obvious, had become uncertain. And, in that uncertainty, in that vertiginous gap between seeming and being, humanity had found a new frontier, a new mystery, a new glass dome to press our faces against, wondering what lay beyond. The story of the simulation hypothesis was still being written. Its next chapters would be composed by physicists searching for signatures of computational structure in the fabric of reality, by philosophers refining the arguments for and against, by technologists building increasingly realistic virtual worlds, by ordinary people wondering, in quiet moments, whether the world around them was quite what it appeared. Behind the glass dome, the answer waited. Perhaps it would be found. Perhaps it would remain forever hidden. Perhaps the seeking itself was the point, the eternal human impulse to understand, to question, to refuse to accept appearances as final truth. The dome remained in place, clear and curved and encompassing. Through it, reality continued to present itself, consistent and detailed and convincing. And we continued to live within it, to love and work and dream, whether in base reality or simulation, whether fundamental or computed, whether original or rendered. The question persisted. The wonder remained. And, somewhere, perhaps, someone or something watched the watchers, curious about what we would do next, waiting to see if we would ever find the edges of the dome, ever discover the nature of the glass, ever glimpse what lay beyond.